Hello all. So today we are starting in chapter 4 talking about carbohydrates, the main energy food, and hopefully debunking some of the present day knowledge or stuff that's out talking about the low carbohydrate diets. So if we look at dietary carbohydrates, as noted in chapter 3, the major role of carbohydrates in human nutrition is to provide energy, and scientists have long known that carbohydrate is one of the prime sources of energy during exercise. Of all the nutrients we consume, carbohydrate has received the most research attention in addition to a potential influence upon athletic performance, particularly in exercise tasks characterized by endurance, such as long-distance running, cycling, and triathloning. Such research is important to athletes who are concerned about optimal carbohydrate nutrition during training and competition. Indeed, continued research over the past quarter century has enabled sports nutritionists to provide more specific and useful responses to athletes' questions. In this chapter, we will explore the nature of dietary carbohydrates, their metabolic fates and interactions in the human body, their possible influence upon health status, and their potential application to physical performance, including the following: the adverse effects of low carbohydrate diets, the value of carbohydrate intake before, during, and after exercise, the efficacy of different types of carbohydrates, the role of carbohydrate loading and carbohydrate foods or compounds with alleged ergogenic properties. Although the role of sports drinks containing carbohydrate, such as Gatorade and Powerade, is introduced in this chapter, additional detailed coverage of these beverages and their effect upon performance is presented in chapter 9. Where we'll be talking about water, electrolytes, and temperature regulation. So, what are the different types of dietary carbohydrate? Carbohydrates represent one of the least expensive forms of calories and hence are one of the major food supplies for the vast majority of the world's peoples. They are one of the three basic energy nutrients formed when the energy from the sun is harnessed in plants through the process of photosynthesis. Although the energy content of the various forms of carbohydrate varies slightly, each gram of carbohydrate contains approximately 4 calories. Carbohydrates are organic compounds that contain carbon, hydrogen, and oxygen in various combinations. A wide variety of forms exist in nature and in the human body, and novel manufactured carbohydrates, including sports drinks, have been developed for the food industry. In general terms, the major categories of importance to our discussion are simple carbohydrates, complex carbohydrates, and dietary fiber. Simple carbohydrates, which are usually known as sugars, can be divided into 2 categories: disaccharides and monosaccharides. Saccharides means sugar or sweet. The 3 major monosaccharides, single sugars, or glucose, fructose, and galactose. Glucose and fructose occur widely in nature, primarily in fruits as free monosaccharides. Glucose is often called dextrose or grape sugar, while fructose is known as levulose or fruit sugar. Galactose is found in milk as part of lactose. Here you'll see in the figure 4.1 the chemical structure of the 3 monosaccharides depicted in both the linear and ring configurations. In each corner in the ring structure contains a carbon atom for a total of 6 carbons for each monosaccharide. So what are the different types of carbohydrate? There's complex carbohydrates, commonly known as starches, that are generally formed when 3 or more glucose molecules combine. This combination is known as a polysaccharide, when more than 10 glucose molecules are combined and may contain thousands of linked glucose molecules. Starches, which exist in a variety of forms such as amylose, amylopectin, and resistant starch, are the storage form of carbohydrates. The vast majority of carbohydrates that exist in the plant world are in polysaccharide form. Of prime interest to us are the plant starches, through which we obtain a good proportion of our daily calories along with a wide variety of nutrients, and the animal starch glycogen, about which we shall hear more later in relation to energy for exercise. Additionally, glucose polymers are polysaccharides prepared commercially by controlled hydrolysis of starch. Maltodextrins are common glucose polymers used in sports drinks, which are discussed later. Unfortunately, because of disagreements over the classification of various forms of carbohydrate, the term complex carbohydrate does not appear on the nutrition facts food label. You may obtain a rough estimate of the complex carbohydrate content by subtracting the grams of sugar from the grams of total carbohydrate. In some cases, the term other carbohydrates is used, which could include complex carbohydrates and other forms of carbohydrates as well. There are different types of dietary fiber. Fiber is a complex carbohydrate. In its recent report on dietary reference intakes, the National Academy of Sciences settled on 3 terms to define fiber. Dietary fiber consists of non-digestible carbohydrates and linen that are intrinsic in intact plants. This would include resistant starch. Functional fiber consists of isolated, non-digestible carbohydrates that have beneficial physiological effects in humans. Total fiber is the sum of dietary fiber and functional fiber. These non-digestible substances, which means that they are not digested and absorbed in the human small intestine, are usually a mixture of polysaccharides found in the plant wall or intracellular structures. The National Academy of Sciences carefully defines both dietary and functional fiber, particularly as they may affect health. In essence, dietary fiber is consumed as part of intact foods, even if mechanically altered, containing other macronutrients such as digestible carbohydrate and protein. For example, cereal brands derived from whole grains contain carbohydrate and protein along with non-digestible fiber. Some examples of dietary fiber are cellulose, hemicellulose, linen, pectin, and gums. When studying the health effects of dietary fiber, it is difficult to determine if health benefits are attributed to dietary fiber or to other potential healthful substances, such as certain phytochemicals found in the food. The definition of dietary fiber includes the phytochemicals that come with it. Functional fibers, in contrast, may be isolated or extracted from foods by chemical or other means and may be manufactured synthetically. For example, various gums may be extracted from seeds and used as food ingredients for various purposes. Some examples of functional fiber are pectin, gums, and resistant starch. The specific fiber has to demonstrate a physiological effect in the body to be classified as a functional fiber, and this effect may be associated with a specific health benefit. Total fiber is the sum of dietary fiber and functional fiber. A specific fiber may be classified as both dietary fiber and functional fiber. For example, cellulose can be classified as a dietary fiber as a natural ingredient of an intact food, or it may be considered to be a functional fiber if extracted from a natural source and added to another food. Previously, the various components of dietary and functional fiber have been classified on the basis of their solubility in water. Some fibers have been referred to as water-soluble because they have been found to dissolve or swell in water and may be metabolized by bacteria in the large intestine. Others that do not possess these characteristics have been referred to as water-insoluble fibers. Common water-soluble fibers include gums, beta-glucans, and pectins. Common water-insoluble fibers include cellulose, hemicellulose, and linen. Each of these types of fibers may confer specific health benefits, which will be discussed later in this chapter. This is just a summary of the different types of carbohydrates and the effects of different forms of carbohydrate on physical performance or health are presented later in the chapter. So what are some common foods high in carbohydrate content? 3 of the 6 food exchanges are the primary contributors of carbohydrate in the diet per serving. The starch exchange contains 15 grams, the fruit exchange 15 grams, and the vegetable exchange 5 grams. Some foods in the meat and milk groups also contain moderate to high amounts of carbohydrate. Dried beans and peas, because of their protein content, is comparable to that of meat and may be listed in the meat and meat substitute group. 1/3 cup of navy beans contain 15 grams of carbohydrate, which is nearly 70% of its energy content. A glass of skim milk contains 12 grams of carbohydrate, more than 50% of its energy content. Table 4.2 shows some foods in the different food exchange that have high carbohydrate content. A more extensive listing is provided in Appendix X. Complex carbohydrate foods are accentuated as they are highly recommended in the healthy healthy diet. Miscellaneous foods such as sodas, fruit aids, candy, pies, cake, and other processed foods are high in carbohydrates. Added sugars is the term applied to refined sugars that are added to foods during production. Reading food labels will provide you with the total amount of carbohydrates in grams, grams of sugar, and grams of fiber. The label will also provide you with the percentage of your recommended daily value for total carbohydrate and fiber. As carbohydrates are the major fuel for most exercise tasks, several products have been marketed to athletes, particularly sports drinks, sports gels, and sports bars. Sports drinks such as Gatorade, and Powerade usually contain about 6 to 8% carbohydrates, or about 4 to 18 grams of carbohydrate per 8 fluid ounces. The carbohydrate source in each varies, but usually contains a mixture of one of the following: glucose, fructose, sucrose, and glucose polymers. More details on sports drinks are presented in Chapter 9. Sports gels such as Reload, GU, Power Gel, and Cliff Shot contain forms of carbohydrates similar to those used in sports drinks, but in a more solid gel form. They come in small squeeze containers, usually about 1 ounce, and contain roughly 20 to 30 grams of carbohydrate. Energy chews are a recent alternative for endurance athletes. They come in packets of 3 to 10 chews containing 2.3 to 8 grams of carbohydrate per piece. Sports bars are also high in carbohydrate, usually with small amounts of protein and fat. The amount and type of carbohydrate per bar vary, the amount generally ranging between 20 to 45 grams. So-called energy drinks may contain substantial amounts of carbohydrate, often 30 to 50 or more grams in 8 ounces. Again, nutrition facts, food labels on sports and energy drinks, sports gels, and sports bar provide information on the nutrient content, including amount of total carbohydrate, sugar, and fiber, as well as other ingredients such as caffeine, amino acids, vitamins, and minerals. By careful label reading and price comparisons, you may be able to get a better buy on some products. For example, sports bars are rather expensive, so purchasing lower cost granola bars that contain similar nutrient value may provide some financial savings. Foods high in dietary fiber include most vegetables and fruits, foods in the starch exchange made from whole grains, and dried beans and peas in the meat exchange. Wheat products are good sources of insoluble fiber, while oats, beans, dried peas, fruits, and vegetables are excellent sources of soluble fiber. Because of the purported health benefits of fiber, cereal manufacturers have released new products containing 13 to 14 grams of fiber per serving. Psyllium, rich in both soluble and insoluble fiber, is now added to several breakfast cereals. Table 4.3 represents the average fiber content in some common foods. Food labels also document fiber content per serving. Currently, food labels document total fiber content per serving, but future labels may contain both dietary and functional fiber content. How much carbohydrates do we need in the diet? As we shall see, the human body can convert part of dietary protein and fat to carbohydrate. Thus, the National Academy of Sciences indicated that the lower limit of dietary carbohydrate compatible with life apparently is 0, provided that adequate amounts of protein and fat are consumed. Several populations around the world have subsisted on a diet with minimal amounts of carbohydrate without any apparent adverse effects. However, given that a very low carbohydrate diet may be associated with various micronutrient deficiencies and health problems in Western societies, dietary reference intakes, or DRI, recently have been developed for carbohydrate and total fiber and may be found in the DRI table for macronutrients on the front inside cover. The RDA for carbohydrates is set at 130 grams per day for adults and children, which is based on the average minimum amount of glucose utilized by the brain. Pham and others noted that although the brain constitutes only 2% of body mass, its metabolism accounts for 50% of total body glucose utilization. The Academy developed an acceptable macronutrient distribution range, or AMDR, recommending that 45 to 65% of the daily energy intake be derived from carbohydrate. The AMDR for individuals have been set for carbohydrate based on scientific evidence suggesting such an intake may play a role in the prevention of increased risk of chronic diseases and may also ensure sufficient intake of essential nutrients. Most of us consume carbohydrate within this range and meet the RDA, as men consume an average 200 to 330 grams per day, while women average 180 to 230 grams per day. The daily value, or DV, for carbohydrate on the food label is based on a recommendation of 60% of the caloric intake. The daily value for a 2,000 calorie diet is 300 grams of carbohydrate, which represents 60% of the daily caloric intake. If you take 4 times 300, it equals 1,200 carbohydrate calories. 1,200 by 2,000, that equals 60%. The Academy recommends an adequate intake for total fiber as follows. For men, about 38 grams up to age 50. 30 grams for over age 50. So as you age, grams are going to increase, or the fiber will decrease, For women, 25 grams up to age 50, and then 21 grams over the age of 50. The daily value, or DV, for a 2,000 calorie diet is 25 grams of fiber, or 12.5 grams per 1,000 calories. Thus, the daily value is in accord with the AI for women, but somewhat lower than the AI for men. The current average amount of total fiber intake is approximately 15 grams per day. So most individuals are not meeting this recommendation. An increased intake of complex carbohydrate will help meet this recommendation. Inadequate intake of dietary carbohydrate can have a negative effect on physical performance. Foods high in dietary fiber include most vegetables and fruit, foods in the starch exchange made from whole grains, and dried beans and peas in the meat exchange. Wheat products are good sources of insoluble fiber, while oats, beans, dried peas, fruits, and vegetables are excellent sources of soluble fiber. Because of the purported health benefits of fiber, cereal manufacturers have released new products containing 13 to 14 grams of fiber. Psyllium, rich in both soluble and insoluble fiber, is now added to your breakfast cereals. Food labels also document fiber content per serving. Currently, food labels document total fiber content per serving, but future labels may contain both dietary and functional fiber content. Sports nutritionists also recommend a high carbohydrate diet for individuals engaged in athletic training programs. The general recommendations for most athletes parallel the recommended dietary goals noted above. For an athlete consuming 3,000 calories per day, 55 to 60% from carbohydrate would be 1,650 calories to 1,800 calories, or about 400 to 450 grams. Ron Mon and Louise Burke, experts in sports nutrition, have described how carbohydrate intake varies considerably based on the specific needs related to physical activity levels, sport, and individual goals. Thus, the amount of carbohydrate needed by an individual exercising to lose weight will be quite different from the amount needed by an individual in training to run a marathon. These considerations will be discussed later in this chapter and in Chapter 11. Many recent dietary surveys conducted with athletes, including endurance athletes, often reveal a carbohydrate intake is significantly lower than these recommendations. Inadequate intake of dietary carbohydrate can have a negative impact on physical performance. So if we look at metabolism and function, the food we eat must be processed before the nutrients it contains may be used in the body for their various purposes. The process includes digestion, absorption, and excretion of nutrients, which is the responsibility of the gastrointestinal or GI system or alimentary canal, which extends from the mouth to the anus. Figure 4.2 presents the main organs involved in the GI system, some of their basic digestive functions, and the sites of nutrient absorption, which will be discussed in the following chapters. So digestion is the process by which food is broken down mechanically and chemically in the digestive tract and converted into absorbable forms. Specific enzymes break down food into smaller substances that may be absorbed. Specific enzymes of interest regarding carbohydrates, fats, and protein will be discussed where appropriate. Absorption of nutrients, as noted in Figure 4.2, may occur in the stomach and large intestine, but the vast majority of nutrients are absorbed through the millions of villi lining the small intestine. Some substances are absorbed by diffusion, which may be passive or facilitated. In passive diffusion, the substance simply diffuses across the cell membrane. Osmosis is the passive diffusion of water. In facilitated diffusion, a receptor in the cell membrane is needed to transport the substance from the intestine to the villi. No energy is required for diffusion, but other substances need energy supplied by the villi cells in order to be absorbed, a process known as active transport. Figure 4.3 represents a cross-section of a villus and highlights some of the key nutrients in the associated process of absorption. And Figure 4.2 here, it shows the alimentary canal includes the mouth, the esophagus, the stomach, the small intestine, which includes the duodenum, the jejunum, and the ileum. The large intestine, or the colon, the rectum, and the anal canal. Various glands and organs, including the salivary glands, the gallbladder, and the pancreas, secrete enzymes and other constituents into the digestive tract. Most blood draining from the intestines goes to the liver for processing. Note the general sites in the digestive tract where principal nutrients and other absorption substances are absorbed. Although there is some overlap in the exact site of absorption, most absorption of nutrients occurs through the small intestines. This is the basic structure of the villus, and millions of villi in the small intestine absorb the digested nutrients. Most nutrients are absorbed into the capillaries and are transported in the blood. Fats are absorbed primarily in the lacteal, being transported to the lymph vessels and eventually into the blood. Nutrients are absorbed into the body in various ways. Water enters the cell by osmosis, most fatty acids by diffusion, and amino acids via active transport, a process that requires energy. Monosaccharides and electrolytes may use two pathways, either diffusion and active transport. How are dietary carbohydrates digested and absorbed, and what are some implications for sports performance? Carbohydrates usually are ingested in the forms of polysaccharides, which are starches, and disaccharides, sucrose, maltose, and lactose, and monosaccharides, glucose and fructose. In addition, special carbohydrate compounds such as glucose polymers have been developed for athletes. To be useful in the body, these carbohydrates must be digested, absorbed, and transported to appropriate cells for metabolism. The digestion and absorption of dietary carbohydrates are highlighted in Figure 4.4. The enzymes that digest complex carbohydrate is amylase, which is secreted by the salivary glands and pancreas. Saliva amylase initiates digestion of the polysaccharides to disaccharides, but most digestion is done in the small intestine by pancreatic amylase. Enzymes then digest the disaccharides to monosaccharides, which are absorbed by specific receptors in the villi. What happens to the carbohydrate after it is absorbed into the body? Of the three monosaccharides, glucose is of most importance to human physiology. Most dietary carbohydrates are broken down to glucose for absorption into the blood, while the majority of the absorbed fructose and galactose are converted to glucose by the liver. Glucose is the blood sugar. The glycemic index, or GI, represents a ranking system relative to the effect that consumption of 50 grams of a particular carbohydrate food has upon the blood glucose response over the course of 2 hours. The normal baseline measure is 50 grams of glucose, and the resultant blood glucose response is scored as 100. So if we look at the glycemic index, it is in general a ranking system relative to the effect consumption of 50 grams of specific carbohydrate has on blood glucose. The blood glucose response to 50 grams of glucose is ranked at 100. So in general, if they have 70 or more, that is considered to be a high GI or glycemic index food. If it's 55 to 69, that's a medium GI food. And 55 or less is considered to be a low GI food. If we look at glycemic load, that is another representation of a ranking system relative to the effect that eating a carbohydrate food has on the blood glucose level, but GL also includes the portion size. So while the glycemic index is based on 50 grams of a particular food, a typical serving sizes for that food may be 6 to 8 ounces or 180 to 240 grams. So the GL is calculated by the following formula. And the following values are used to rank the glycemic load of foods. So 20 or more is a high glycemic load food. 19 to 11 is a medium glycemic load food. And 10 or less, low glycemic food. The glycemic load is glycemic index times gram of non-fiber carbohydrate in one serving divided by 100. And the GL for some foods is presented here in table 4.4. Many factors other than a food's carbohydrate content, such as the physical form, coarse or fine, and serving mode, raw or cooked, may influence the glycemic index of any given food. Moreover, the glycemic index for any given food may vary considerably between individuals, so that although some general values of the glycemic index may be given, the effects of different foods should be tested individually in those who are concerned about their blood sugar levels. In general, foods containing high amounts of refined sugars have a high glycemic index because they lead to a rapid rise in the blood sugar, but some starchy foods also have a high glycemic index. In contrast, foods high in fiber such as beans generally have a low glycemic index. Interestingly, fructose has a low glycemic index, which is one of the reasons its use as the primary carbohydrate source in sports drinks have been advocated for endurance athletes. We'll discuss the role of fructose later in this chapter. Table 4.4 classifies some common foods according to their glycemic index. So the usefulness of glycemic index and glycemic load is the subject of debate. As reviewed by Mirahimi and by Greenwood, glycemic index may play a role in reducing cardiovascular disease risk and exercise performance is at an early stage. Disease risk and diabetes, respectively. O'Reilly notes that research on glycemic index and exercise performance is at an early stage, but may have some benefit. However, Sachs and others recently demonstrated that when a large group of overweight adults were placed on a 5-week high or low glycemic index diet, the high glycemic index diet did not improve insulin sensitivity, systolic blood pressure, LDL, or HDL cholesterol. The strength of this study is that food for the diets, all meals, snacks, and calorie-containing beverages were provided by the investigators for 5-week diets. The authors suggest that selecting foods based on glycemic index may not improve cardiovascular risk factors or insulin resistance. As noted, one person's glycemic response to a given food may be very different from someone else's response. Moreover, individuals do not normally consume carbohydrate foods by themselves, but usually with other foods containing fat and protein, such as a hamburger on a bun. The addition of fat and protein will usually reduce the glycemic index and glycemic load. The glycemic index and glycemic load can be used to help select more healthful carbohydrates. In general, the lower the glycemic index and glycemic load, the more healthful the source of carbohydrate. And this is just another additional chart there. So, what is the metabolic fate of blood glucose? Normal blood glucose, or normoglycemia, range between 80 and 100 milligrams per deciliter of blood. The maintenance of a normal blood glucose level is very important for proper metabolism. Thus, the human body possesses a variety of mechanisms, primarily hormones, to help keep blood glucose levels under precise control. The rise in blood glucose, also known as serum glucose, stimulates the pancreas to secrete insulin into the blood. Insulin is a hormone that facilitates the uptake and utilization of glucose, facilitated diffusion by various tissues in the body, most notably the muscles and adipose or fat tissue. Cell membranes contain receptors to transport glucose into the cell. The primary receptors in muscle and fat cell membranes are known as GLUT4 receptors, which are directly activated by insulin. Exercise also activates these receptors to transport blood glucose into the muscle cell, independently of the effect of insulin. Other hormones discussed later in this chapter are also involved in regulating blood glucose. With normal amounts of carbohydrate intake in a mixed meal, blood glucose levels remain normal. So the primary receptors in a muscle and fat cell membrane are known as GLUT4 receptors, which are directly activated by insulin. And you can see the transporters here without insulin and with insulin. Insulin promotes the transport of glucose across the plasma membranes. This is done by the recruitment of intracellular vesicles containing glucose transporters, or GLUT proteins, to the plasma membrane, where they facilitate glucose diffusion to the cell. GLUTs are stored in these membrane-bound vesicles inside the cell, but there are a few in the plasma membrane as well. This figure demonstrates the glucose transporter proteins without insulin. Exercise also activates these receptors to transport blood glucose into the muscle cell independently of the effect of insulin. Other hormones discussed later in the chapter are also involved in regulating blood glucose. With normal amounts of carbohydrate intake in a mixed meal, blood glucose levels remain normal. So with insulin, vesicles fuse with the plasma protein, exposing more GLUTs to the extracellular fluid, and more glucose is taken up by the cell. Now, if we look at the fates of blood glucose, foods with high glycemic index may lead rapidly to high blood glucose levels, possibly hyperglycemia, which is greater than 140 milligrams percent, which will cause an enhanced secretion of insulin from the pancreas. High serum levels of insulin will then lead to a rapid and possibly excessive transport of blood glucose into the cells. This may lead in turn to hypoglycemia, which is less than 40 to 50 milligrams percent, or low blood glucose level. This insulin response and reactive hypoglycemia following carbohydrate intake may be an important consideration for some athletes, and is discussed later. Foods with a low glycemic index, particularly soluble fiber forms, lead to a slower insulin response and a more stable blood glucose level. Consuming a diet based on the glycemic index has been studied as a possible means to enhance health, as well as sports performance. The fate of blood glucose is dependent upon a multitude of factors, and exercise is one of the most important. The following points represent the major fates of blood glucose schematically. So you can see, after assimilation into the blood, glucose may be stored in the liver or muscles as glycogen, or may be utilized as a source of energy by these and other tissues, particularly the nervous system. Excess glucose may be partially excreted by the kidneys, but major excesses are converted to fat and stored in the adipose or fat tissues. So you can see, first, blood glucose may be used for energy, particularly by the brain and other parts of the nervous system that rely primarily on glucose for their metabolism. Hypoglycemia can impair the normal function of the brain. Although hypoglycemia as a clinical condition is quite rare in the general population, transitory hypoglycemia may occur in very prolonged endurance exercise. Really just means that you're not getting enough calories or enough carbohydrates. Secondly, blood glucose may be converted to either liver or muscle glycogen. It is important to note that liver glycogen may later be reconverted to blood glucose. However, this does not occur to any appreciable extent with muscle glycogen. In essence, glucose is locked in the muscle once it enters, owing to the lack of a specific enzyme needed to change its form so that it can cross the cell membrane back into the bloodstream. Most of the muscle glycogen is converted to this locked form of glucose during the production of energy. Researchers discovered two forms of muscle glycogen, proglycogen and macroglycogen. Hargraves indicates that the functional significance of these glycogen forms remains to be fully elucidated. Houston indicates that the proglycogen seems to be preferentially used during muscle activity, while the macroglycogen may be more of a reserve supply of carbohydrate for prolonged exercise. In this text, we shall use the term glycogen to represent both forms. And then thirdly, blood glucose may be converted to and stored as fat in the adipose tissue. This situation occurs when the dietary carbohydrate, in combination with caloric intake of other nutrients, exceeds the energy demands of the body and the storage capacity of the liver and muscles for glycogen. Some blood glucose also may be excreted in the urine if an excessive amount occurs in the blood because of rapid ingestion of simple sugars. So how much total energy do we store as carbohydrate? A common method to express the concentration of carbohydrates stored in the body is in millimoles. A millimole is 1/1000 of a mole, which is the term representing gram molecular weight. In essence, a mole represents the weight in grams of a particular substance, such as glucose. The chemical formula for glucose is C with 6 substrates, hydrogen, and oxygen. So it contains 6 parts of carbon and oxygen and 12 parts of hydrogen. The atomic weight of carbon is 12. Hydrogen is 1 and oxygen is 16. If you multiply the number of parts by the respective atomic weights of each of the elements for glucose, 6 times 12, 12 times 1, plus 6 times 16, you get a total of 180. Thus, 1 mole of glucose is 100 grams, or about 6 ounces. 1 millimole is 1 divided by 1,000 of 180 grams, or 180 milligrams. These calculations have been presented here because this is the means whereby concentrations of glucose, glycogen, and other nutrients are expressed in contemporary scientific literature. A knowledge of these mathematical relationships should help you interpret research more effectively. However, because we are using the calorie as a measure of energy in this book, and because each gram of carbohydrate equals approximately 4 calories, an estimate of the energy content of the major human energy sources of carbohydrate may be obtained. For our purposes, the body has 3 major energy sources of carbohydrate: blood glucose, liver glucose, and muscle glycogen. Some glucose, about 10 to 15 grams, is also found in the lymph and intercellular fluids. Initial stores of blood glucose are rather limited, totaling only about 5 grams, or the equivalent of 20 calories. However, blood glucose stores may be replenished from either liver glycogen or absorption of glucose from the intestine. The liver has the greatest concentration of glycogen in the body. However, because its size is limited, the liver normally contains only about 75 to 100 grams of glycogen, or 300 to 400 calories. 1 hour of aerobic exercise uses more than half of the liver glycogen supply. It is also important to note that the liver glycogen content may be decreased by starvation or increased by a carbohydrate-rich diet. 15 hours or more of starvation will deplete the liver glycogen, whereas certain dietary patterns may nearly double the glycogen content of the liver, a condition that may be useful in certain tasks of physical performance. The greatest amount of carbohydrates stored in the body is in the form of muscle glycogen. This is because the muscles compose such a large portion of the body mass as contrasted to the liver. One would expect large differences in total muscle glycogen content between different individuals because of differences in body size. However, for an average-sized untrained male with about 30 kilograms of his body weight consisting of muscle tissue, one could expect a total muscle glycogen content of approximately 360 grams, or 1,440 calories. This would represent a concentration of about 66 millimoles, or 12 grams per kilogram of muscle tissue. As with liver glycogen, the muscle glycogen stores also may be decreased or increased with considerable effects on physical performance. For example, a trained endurance athlete may have twice the amount of stored muscle glycogen than an untrained sedentary individual has. If we calculate the body's storage of carbohydrate as blood glucose, liver glycogen, and muscle glycogen, the total is only about 1,800 to 1,900 calories, not an appreciable amount. 1 full day of starvation could reduce it considerably. Some normal ranges of carbohydrate stores are presented in Table 5, although these normal ranges may be increased or decreased considerably by diet or exercise. So can the human body make carbohydrates from protein and fat? Because the carbohydrate stores in the body are rather limited, and because blood glucose is normally essential for optimal functioning of the central nervous system, it is important to be able to produce glucose internally if the stores are depleted by starvation or a zero carbohydrate diet. This process in the body is called gluconeogenesis, meaning the new formation of glucose. A number of different substrates from each of the 3 energy nutrients may be used and or depicted graphically. Protein may be a significant source of blood glucose. Protein breaks down to amino acids in the body, and certain of these amino acids, notably alanine, may be converted to glucose in the liver. This is referred to as the glucose-alanine cycle, which is explained further in Chapter 6. A number of other amino acids also are gluconeogenic. Glucose is essential for the brain and several other tissues. If about 130 grams of carbohydrate are not consumed daily, then the body will produce the glucose it needs, primarily from protein in the body. So fats in the body break down into fatty acids and glycerol. Although there is no mechanism in human cells to convert the fatty acids to glucose, glycerol may be converted to glucose through the process of gluconeogenesis in the liver. Through gluconeogenesis, 1 gram of protein will yield about 0.56 gram of glucose. Triglycerides are about 10% glycerol, and each gram of glycerol may be converted to a gram of glucose. In addition, certain byproducts of carbohydrate metabolism, notably pyruvate and lactate, may be converted back to glucose in the liver. Some of the lactic acid produced in the muscle during intense exercise may be released into the blood and carried to the liver for reconversion to glucose. The glucose may then return to the muscles to be used as an energy source or stored as glycogen. This is the Cori cycle. It's noted in Figure 4.9, which illustrates some of the basic interrelationships among carbohydrate, fat, and protein in human nutrition. This is gluconeogenesis. You can see the liver is the major site for gluconeogenesis in the body. The breakdown products of fats, proteins, and carbohydrate from other parts of the body may be transported to the liver by the blood for eventual reconversion into glucose. Glycerol, glucogenic amino acids, lactate, and pyruvate may be important sources for the formation of glucose. The Cori cycle involves the transport of lactate to the liver and conversion to glucose, which may then be transported back to the muscle. So what are the major functions of carbohydrate in human nutrition? The major function of carbohydrate in human metabolism is to supply energy. Some body cells, such as the nerve cells in the brain and retina and the red blood cells, are normally totally dependent upon glucose for energy and require a constant source. Through a series of biochemical reactions in the body cells, glucose is oxidized, eventually producing water, carbon dioxide, and energy. Zierler notes that although carbohydrate is an excellent source of energy, it is not the major fuel when the body is at rest. Fats are. Carbohydrate is the main fuel for certain tissues during rest, such as the brain, central nervous system, and red blood cells, but provides only about 15 to 20% of muscle energy needs during rest. Thus, the body conserves its limited carbohydrate stores by using fats as the primary energy source during resting conditions. As noted in Chapter 3, carbohydrate can be used to produce energy either aerobically or anaerobically. Recall that in the lactic acid system, ATP is produced rapidly via anaerobic glycolysis, but for this system to continue functioning, the end product of glycolysis, pyruvic acid or pyruvate, must be converted into lactic acid. In the oxygen system, aerobic glycolysis predominates, and pyruvic acid is converted into acetyl-CoA, which enters into the Krebs cycle and electron transfer system for complete oxidation and the production of relatively large amounts of ATP. For the same amount of carbohydrate, anaerobic metabolism yields only 2 ATP, whereas aerobic metabolism yields 36 to 38 ATP. Carbohydrates have some functions in the body other than energy production. Monosaccharides can be used to form other smaller carbohydrate molecules such as trioses and pentoses. These substances may combine with other nutrients and form body chemicals essential to life, such as glycolipids or glycoproteins. Glycoproteins are very important components of cell membranes, serving as receptors to help regulate cell function. Ribose is a key pentose that is a part of a number of indispensable compounds in the body. One of those compounds is RNA, or ribonucleic acid, which plays an important part in anabolic processes in the cells. Figure 4.9 demonstrates interrelationships among carbohydrate, fat, and protein metabolism in humans. All three nutrients may be utilized for energy, although the major energy sources are carbohydrate and fat. Excess carbohydrate may be converted to fat. The carbohydrate structure also may be used to form protein, but nitrogen must be added. Fat cannot be used to generate carbohydrate to any large extent because acetyl-CoA cannot be converted to pyruvate. The glycerol component of fat may form very small amounts of carbohydrate. Fats may serve as a basis for the formation of protein, but again, nitrogen must be added. Excess protein cannot be stored in the body, but can be converted to either carbohydrate or fat. And that concludes our discussion today. We'll pick up again. We'll be continuing Chapter 4 in carbohydrates again tomorrow. Thanks so much. Talk to you soon.